Kenapa macam ni? Recap from part 2. Okay, so don't get confused between adiabatic and non-adiabatic. Okay, and also isothermal. Okay, so adiabatic, the Q is 0. Okay, but non-adiabatic, there is a formula, okay, that you will learn in part 3. And isothermal is applied to the adiabatic and non-adiabatic, which the T is not equal to T naught. Alright, so you have to consider this. Okay, especially when there is an ideal equation, you cannot just cancel T with T naught. Okay, you only can cancel, let's say if the pressure is same, okay, so you boleh cancel lah. Okay, alright, so basically the equation that you need to know, okay, throughout this topic is Q, okay, minus with the WS, okay, FA naught. Nanti I akan terangkan. Let me write down first the equation. T minus T I naught minus with the touch. Theta CP T minus TR. Okay, FA naught X equal to 0. Okay, so this is the general equation that you need to know. Okay, how to use it lah basically. Okay, so if it's adiabatic, alright, and it is isothermal, so what you can apply is this Q is equal to 0. Okay, and let's say there is another assumption that stated that the work sharp, there is no work sharp. So this one you can make it 0. Okay, just you can rearrange the equation. Okay, so here you kena bawa lah this, maybe this part, okay, transfer to the right side here. Okay, whereby the Fn naught kita boleh body call it cancel lah sebab sama term, so Fn naught akan cancel. So what left is this one only part. Okay, so from here actually you can arrange it in term of X ataupun in term of T. Okay, so when you arrange to X, it will become for the conversion for S energy balance. Okay, we have two terms, whether it's in conversion of mass balance ataupun kita panggil that conversion of equilibrium. Okay, another term is XEB. Okay, so this one usually we derive it from design equation lah. Okay, so it can be from reversible ataupun non-reversible. Okay, and also depends juga pada type of reactor. Okay, whether it is a CSTR ke, whether it is PFR and so on. Okay, so XEB is the one that you derive from the energy balance. Okay, so you will have theta I CPI. Okay, just rearrangekan dia. T minus T I naught. Okay, over with the negative delta H Rx TR plus with the delta CP T minus TR. Okay, so actually the bottom part here, denominator, alright, is equals to delta HRX. Okay, so delta H, alright, Rx at T, this is at any temperature, is equal to this one actually, delta H Rx at the T reference plus with the delta CPT minus TR. Okay, so whether you can use this term at any temperature ataupun refer at the reference temperature. Okay, just substitute this part lah. Okay, so this would become the head of reaction term. Okay, this one is become the head of capacity term. Capacity term. Okay, so for pure A, alright, let's say the reaction involve A to B, alright, so pure A enters the reactor, so automatically this would be 0. Okay, so delta Cp is equal to 0. Okay, so you will have this one only. Okay, so the reason we need to get XE and XEB, alright, in order for you to plot the graph, okay, X, okay, versus with the T. Okay, so you're going to have a two curve, alright. So usually the XE is like this. Okay, then we have a XEB, which looks like this one. Okay, so XE ni actually is depending on the whether it is endothermic or exothermic. Okay, so the curve would be different. Sekejap, batuk sekejap. So usually for what do you call it? For exothermic, okay, the XE will looks like this. Okay, ke bawah. Okay, usually this is for exothermic. And another one, we have a what do you call it? Endothermic. Okay, usually dia akan straight here. Dia ke bawah macam straight lah. Okay. Itulah sebenarnya. Okay. So this is X. Dia akan ada lagi satu which is XEB ataupun XE. Okay. So titik yang intercept here. Okay. We call it as a adiabatic conversion and temperature. Alright. This one we got adiabatic equilibrium conversion. Lupa nak tulis equilibrium conversion and adiabatic temperature. Okay. So I tulis balik semula lah. Adiabatic equilibrium conversion. Alright, dekat sini titik dia. And adiabatic temperature. Okay, so this is adiabatic temperature. You akan dapat sini. Okay, TA dia. And this is would be the XE lah. Okay. Okay, so this one also you can expand the equation. Okay, so for example, we have a TR here. Okay, so delta HRX TR will equals to H T product, okay, minus with the H reactant. Okay, and this one also you can expand. Alright, delta CP is equal to CP product minus with the CP reactant. Okay, and then we have a theta ICPI ni pun you kena keluarkan lah. Alright, so untuk produk, theta for product is equal to 0. Okay, so you only consider the reactant part only for theta ni. Okay, so we move to the exercise. Okay, so production of chemical species B is to be carried out adiabatically. Okay, dia dah bagi tahu is adiabatically in a series of continuous reactor, a CSTR followed by PFR. Okay, so meaning that first we have a CSTR. Okay, connect with the PFR. Okay, so the reaction involve A to B and given the heat of the reaction, okay, which is negative 6.9 K Jmol per mole. So the feed to the reactor which composes of 90% A, alright, so it is given YA0 is 0.9, while the remaining is inert entering at temperature of 330 K. So this would be the 3 T0. Okay, with a flow rate of K mole per hour. Okay, so this would be the FA0. The initial concentration of the reactant is 9.3 kilomole per meter cube, which is this is CA0. Given that the conversion of the first reactor is 45%, so X1 is 0.45, and the allowable change of the temperature is between 330 to 370. So this is the T lah, capital temperature. So as an engineer, determine the volume of the first reactor. by using all information provided alongside the aid of 11-speed plot, find the volume of PFR necessary to achieve an overall conversion of 80%. Okay, so if you look at this one, we have a CPA, we have a CPB, CPI for inert, this is a heat capacity, and we have a E for the activation energy, and K is the rate constant. Okay, so what you need to get is the volume. Okay, so first, okay, of course you need to calculate the first volumes, because the first type of reactor is the CSTR. Okay, so you can start with the CSTR. Sorry, this is PFR. Okay, so basically, let's say if we want to get the CSTR volume, okay, so you have to write down first what is the equation involved, which is FA naught, alright, X over negative RA. Okay, so from RA here, okay, you have to expand the equation lah. What is the RA? Okay, whereby this is irreversible. Okay, so it's this is the normal one lah, which is FA naught X is equals to KCA naught 1 minus X. 1 minus X. Okay. Okay, so this will be the equation. Okay, so look at this equation. Okay, what value that you don't have? Okay, for X we already have it, because we want to measure the VCSR, means that we will look at the X1 is equal to 0.5. Okay, so no problem with X. Okay, so you don't have the value of K. So now you have to relate the K now is depend on the temperature. Okay, so how do you relate it? By looking at the Arrhenius equation. Okay, Arrhenius equation is K is equal to K1 exponent, okay, E over R, okay, 1 over T1 minus 1 over T. Okay, so here what you need to do is you need to get the K value. Okay, so once you get the K, you boleh masuk dekat sini. Right? So remember, we have for adiabatic we have case 1 and case 2. Okay, case 1 is when the X or T is specified, while case 2 is for when V is specified. Okay, so in this case we go for case 1. Okay, so what you need to do is, okay, you need to construct the table, okay, for the to get the V. Okay, so okay, so if you look this one, T dia akan, K akan depend pada T. Okay, and T also will depend for the, now this is adiabatic, means it depends on the XEP. Okay, so you have to derive from the equation, okay, whereby XEP is equals to theta CPI T Ti naught, okay, and then the negative theta HRX TR, okay, plus CP T minus TR. Okay, so in this case, okay, you have to get the XEB. Okay, sebab apa? XEB ni, okay, this one you kena letak T, you akan varykan dia. Okay, so T, it stated is must be between 330 until 370. Okay, so you specify the T. Okay, so once you specify the T, you can get XEB. Okay, sama juga, kalau you specify the XEB, you can get the T. Okay, either one only. Okay, so you have to get the XEB here. Okay, buat satu-satu. Alright, for example, we have a E theta I CPI. Alright, so expand the equation. We have a FA naught over with the FT naught. Sorry, FA naught over FA naught. Okay, times with the CPA plus with the FAI. This is for inert over with FA naught. CPI. Okay, macam saya cakap lah, ni kita refer to reactant only. Sebabnya FC0 over with the FA0 is equal to 0. So you don't have to look at the product. Okay, so just calculate, just masukkan balik what is FA0, alright, what is FAI. Okay, so you will able to get around 159 J mole dot K. Okay, so this would be the value. Okay, so delta HRX, okay, since it is given in term of at T, which is delta HRXT, okay, not delta HRXTR, okay, so you don't have to calculate it, this one, okay, so just replace this one with the delta HRXTR, T, sorry, T. Okay, sebab ini kan equal to delta HRXT. Okay, and this one sepatutnya kalau delta CP ni dia kena consider sebab this dia akan jadi lengthy lah equation, sebab that's why in this question terus bagi delta HRX, so you kena calculate delta CP T minus TR sebab sekarang ni dia bukan YA0 dia bukan equals to 1, dia bukan pure fit into the reactor. Okay, it is a 90%. Okay, means that you cannot just simply cancel delta CP. Okay, tapi this one, the whole equation bawah ni, you replace with it delta HRX T. Okay, so just substitute it. Alright. Okay, I simplifykan sajalah. Okay, you need to get XEB is equal to, you kena dapat T minus 330 over with the 43.396. Okay, simplify from this equation. Okay, replacekan saja delta HRX ni, gantikan dengan berapa tadi, 6000 something, berapa sorry, berapa tadi, ni 6900, gantikan bawah ni dengan 6900. Okay, so replace this one lah. Okay, T minus TI0. Okay, so TI0 ni start dengan 330. Okay, so T ni akan berubah ikut yang you varykan this one. Okay, kalau you buat 34, 350, 360, so gantikan dengan T here. Okay, so once you gantikan dengan T, you will be able to get what is XEB. Okay, sebab XEB sekarang ni is equals to T minus 330 43.396. Okay, make sure the sign here must be correct. Okay, sebab kalau sign dah lari, you tak dapat kira XEB tu accordingly. Okay, so once you get the XEB, okay, you also can calculate the K. Alright, sebab K, when you just vary the T here, okay, the information of the E and K1 already given in the question, just substitute the value of the T for the various temperature. Okay, then you will be able to get the negative RA is equal to KCA01 minus XE. Okay, so here you will get it, and you will get the FA0 over negative RA. Okay, so this one kalau nak dapat ni lah, this is PFR. Okay, I cerita ni adalah untuk PFR lah. Okay. Tak ada suara pula. Alright. So daripada situ masukkan balik saja. Kalau VCSTR, just guna VCSTR is equals to FA0 over negative RA times with the X here. Okay. So X here dekat 0.4. This one ganti dengan 0.45. RA here, look at the XE tu berapa. Okay, dekat this one, you just replace dengan ni lah, KCA0 1 minus X. Okay, and then for PFR you kena buat extra work lah. Sebab, remember PFR is the area under the curve. Okay, so this is V. Okay, and then this is FA0 over negative RA, and then we have X here. Okay, so setiap ni you kena bahagikan into a few section. Okay, depending lah pada X you. Alright, so this one you kena construct with respect to XE tau. Okay, so Fn0 over negative RA versus with XE. Okay, so you kena guna numerical method. Okay, so in this case maybe you akan dapat X akan equal to 0.45, X equal to 0.5, X equal to 0.6, X equal to 0.7, X equal to 0.8. Okay, so daripada situ you boleh dapat Fn0 over RA. Okay, so setiap ni you kena gunalah. Okay, katakan this one you can guna trapezoidal. Okay, and this one kita boleh guna Simpson 3-8 rules. Okay, so sum up PFR is around 0.6682 meter cube. Okay, so just construct Fn of RA ni, X ni you ambil daripada XE tu, you buatlah yang ni. Okay, take berapa, so you boleh dapat this one. Teruk ni tulisan saya 0.6682. Okay, so try to calculate it again. Okay, and try to get the final answer same like the one that ni lah yang I give you guys now. Okay, so far the question ke tak? Sebelum I proceed ke soalan number 3.
Ada doktor.
Okay, tak ada. Alright. So proceed to question number 3. Okay, so this one is a reversible case pula. Okay, whereby A to B. Okay, plot of equilibrium conversion as a function of temperature. So dia nak you plot X versus X versus temperature. Okay, so temperature range dia dah bagi between 300 to 500 K. Okay, so this is should be case 1 lah. Okay, dia dah specifykan temperature. Determine the adiabatic equilibrium temperature and conversion when pure A is fed to the reactor at a temperature of 300 K. Okay, so yang ni pula you kena dapat dekat reactor exactly dekat 300 K pula. Okay, temperature. Alright, so what you need to do is, okay, tengok dulu apa information given. So here is the heat capacity is given, and then this is enthalpy. Okay, and if you can see, this is at temperature 298 K, means that this is at T reference. Okay, so basically when it comes to T reference, you kena kira lah delta HRX untuk reference. Okay, kira dia, kena kira. Okay, and then we have a KC. So K here is the capital KC, which is at equilibrium constant. Okay, not the red constant and dot normal one, yang small capital. Alright, so the equation would be involve delta HRX here. Okay, so the difference is in terms of this one. Okay, instead of E, replace with the delta HRX. Okay, you need to do, alright, you need to follow lah the algorithm. Okay, in order for you to get what is the T and XE. Okay, so tengok balik, kita kena construct. Okay, kita ada T. Okay, sebab T is given between 300 to 500. Okay, so ikut you lah, you nak letak sini 330 ke nanti, tapi within the range. Alright, so T ni kalau kita tengokkan dia berkaitan dengan KE ataupun KC tu pun boleh, KE pun boleh. Okay, ikutlah mana nak guna, tapi I letak KE lah sebab nanti nak derive red law daripada equilibrium, so I letak sini KE. Alright, so KE ni akan berubah bila T berubah. Okay, you akan tengok sini lah, here. Okay, and then kita tengok KE dia akan berkaitan dengan KE ni, dia akan berkaitan dengan XE. Sebab apa? That's why you kena buat algorithm dia dulu. Okay, so sekarang ni first you kena derive lah what is the red law. Okay, red law dia akan jadi K negative RA is equal to K CA minus CB over KE. Okay, this is reversible lah. Okay, you kena tunjuk lah macam dapat ni. Okay, sebelum ni I dah tunjuk macam mana you kena kira untuk forward dengan reverse, you kena dapat RA net. Okay, so rearrangekan, dapatkan nilai dari segi K macam ni. Okay, sebab KE is equals to KF over KR. Okay, K forward over ni lah reverse. Okay, so at equilibrium, okay, dekat equilibrium, okay, negative RA is equal to 0. Okay, when it is equilibrium. Okay, therefore, you kena this one 0. Alright, so dia akan jadi sini 0. So, automatically this one akan jadi CAE lah. CAE is equal to CB over KE. Okay, rearrange daripada sini. Okay, then nombor 3, kita kena buat stoichiometry. Okay, stoichiometry. Okay, so bila this is CSTR, so kita assume volumetric flow rate dia adalah sama at any T. Alright, so just substitute lah. So this one kena pecahkan dia in term of the conversion, which is CA naught 1 minus XE, and then CBE, this is product, so CA naught times this XE over KE. Okay, so kita solve for KE, kita combinekan semua ataupun solve for KE, just rearrange here. Alright, so this one kita boleh cancel lah. Okay, so you rearrangekan ni, you will get XE is equal to KE T 1 plus KE T. Okay, that's why you need to get the KE first. Okay, then you will be able to get the XE. Okay, so that's why you can tengok satu-satu apa information missing. Ikut pada sequence dia, how to calculate lah. Alright, don't just jump into other equation. Alright, nanti you can you will get lost. Alright, and stuck. Okay, so look at the information equation of the KET. Okay, what you need to get is the delta HRX here. Okay, so calculate lah what is delta HRX. So delta HRX, okay, ataupun kita keluarkan dia delta HR reaction, alright, at TR is equal to untuk delta untuk B, okay, minus B delta untuk A. So negative 60,000 minus with the minus 40,000, you will get this one is equal to negative 20,000 Cal per mole. Okay, so just masukkan balik this one dekat equation tu, you will get KET equals to 100,000 exponent negative 20,000 over 987 1 over 298 minus 1 over T. Okay, so T1 is referring to at initial temperature lah ataupun T reference dia lah, okay, which is 298 K. Okay, so you will have a different KE at different temperature and also XE at different KE. Alright, so just masukkan balik. Okay, remember the question asks you to get what is adiabatic equilibrium temperature and conversion. Okay, so this is related to so you kena plot dululah ni versus T for the first question. For A, you kena plot X versus with the T. Okay, plot. This would be the first. Okay, so for the second one, B, okay, let's say it is a pure A. Alright, so and you need to get the what is adiabatic equilibrium temperature and conversion. Okay, when there is the word adiabatic equilibrium temperature and conversion, means that you need to have the intersection between two curves. Okay, which is you need to have a XE, alright, and also XEB. Okay, so this is the intersection. This is what we call adiabatic conversions of XEA and also TA. Okay, you need to get this value. Okay, so you already have the XE. Okay, you don't have to bother. Now you just add one more for XEB. here. Okay, so what is XEB? Okay, this is the one that I simplify. XEB is equals to theta delta I CPI, alright, T minus T naught over with the negative delta HRX TR lah. Okay, sebab dia plus CP tu dah cancel. Sebab dia adalah delta CP sekarang is equal to 0 sebab dia pure air. Alright. So daripada situ just substitute the value. Okay, you will get XEB is equals to 500 T minus with the 300, okay, over with the 20,000. Okay, so basically XE is equal to 0.41, alright, and TE you akan dapat around 465K. Okay, so I nak cakap awal-awal untuk final assessment, you kena sediakan kertas graf everyone kena sedia ada set 1 and set 2, and dua-dua set require you to do a you kena buat graf. Okay, so make sure you have, I dah beritahu awal ni, you boleh start lah beli untuk kertas graf. Okay, kertas graf tu nanti you kena buat manual calculation kat situ, kena plot graf semua tu lah. Okay, you cannot use Excel. Alright, sebab this one is closed-ended, closed book examination. Okay, so far faham up to this point? Before I proceed to part 3. Part 3 sikit je slide, tak banyak pun. Okay, can I proceed?
Proceed.
Okay, alright. Okay. Okay, baca email penting lah. Okay, so part 3 I dah ni dah upload dalam Teams dah semalam. Okay, so now we move to part 3. Okay, so part 3 is about this subtopic, which is non-adiabatic reactor design. Okay, whereby you need to learn about reactor staging, alright, which is you may install a stage cooling or heating between the reactors in order to cool it down or to heat up, okay, before it enters to the subsequent reactor. And you will learn about CSR with heat exchange, PFR or PBR with heat exchange. Okay, so here you will refer to the same term, which is XE, alright, X equilibrium. Okay, so non-adiabatics means that there is a changes of heat, alright, ada change of heat between reactor and surrounding. And its surrounding. Okay, and also apply for isothermal, non-isothermal. Okay, so that's why there is a Q. Okay, you need to consider the Q in the energy balance. Okay, you cannot omit this one. Okay, alright. Okay, so this one lah, number 2. Okay, kita belajar. Okay, so non-adiabatic ni sometimes you in the reactor, okay, for example, you require a coil lah. Okay, so this coil, whether it is a cooling ataupun heating. Okay, sometimes dia dalam reactor ataupun dia put it dekat luar, alright, heater atau cooler dia. Okay, and then ataupun we have another terms. Okay, we have a reactor, usually STR. Okay, so how we maintain the temperature here inside the reactor is we put a jacket. Okay, we call it jacket reactor. So usually some ada this one is made from a wool ke apa ke, ataupun dia akan letak a steam here. Alright, in order to maintain a specific temperature lah in the reactor. Okay. So here you will learn about reactor staging. Okay, if you can see, this is a reactor number 1, and we have a reactor number 2, and we have a reactor number 3. Okay, so this is the symbol for coolant. Alright. Okay, coolant atau ataupun heater. Okay, so this one for exothermic, achieving higher conversion by interstage cooling. Okay, so for exothermic kita akan guna cooling. Okay, in order to get a high XE. Okay, sebab temperature yang rendah, okay, will cause a high XE. Okay, remember graph dia adalah macam ni. Okay, so this is X, this is T. Okay, so lagi tinggi XE adalah dekat T yang rendah. Okay, remember this is the previous graph. Okay, for exothermic. So kalau X T kata 0.9, T dia kena less than T outlet here lah. Okay, so bila dia perlu nak reducekan temperature, what you need is you need to have a interstage cooling. Okay, so instead of before this we didn't learn about reactor staging. Means that, okay, let's say we have a graph here. Okay, this is XE graph. Okay, so if we, okay, let's say this start with T naught. Okay, so if we increase the T here, okay, to at one point, okay, let's say if the T feed ni, they increase to a certain temperature, alright, it will cause a reduction of XE. Okay, that's why we need to introduce a few, what do you call it, a few temperature, alright, ataupun interstage cooling, in order to control the temperature, dia akan naikkan dia, zigzagkan dia. Okay, in order dia nak reach to highest 1 XE. Okay, that's why we introduce interstage cooling. Okay, sebab kita nak manipulate the temperature, alright, instead of we only increase at one temperature only, kita increase at different temperature, various temperature. Okay, sebab dia akan naikkan dia sampai dia reach XE. Okay, kalau kita introduce satu saja, dia akan lowkan XE. Kita nak tinggikan XE. Okay, that's why you kena pushkan dia balik, what do you call it, manipulate again the temperature in order naikkan balik the XEB, manipulate lagi temperature, naikkan XB, and so on. Alright, okay, so that's the reason. Okay, so let's say we have this one. Okay, the inlet is 500 degrees Celsius. Okay, since it release a what do you call it, heat. Okay, exothermic, the heat release heat. Okay, so the effluent tu yang keluar tu akan tinggi temperature. Okay, so the objective for this to get a high XE is to lower the temperature. Okay, that's why we need to have a coolant. Okay, so this coolant will lower the temperature, if you can see, from 800 to 500. Okay, before it enters to the second reactor. Okay, so this is reactor and this is coolant. Okay, so from here, and then after the reaction, at a period of time, alright, it will release a heat, alright, which increase the temperature. Okay, again, in order to increase the XE, we need to lower down the temperature. Okay, so you have to have a cooling system here, reduce it back, alright, before it enters to R3 and so on. Okay, so here you will have an interstage. Okay, starting for 500, okay, if you can see, to 800. So it will reach at certain X here, alright, and then we have a interstage cooling, whereby from 800 here, we reduce to 500. Alright, in order for the reactor number 2 to have an increase of XE. Okay, so this is yang sengit ni, diagonal ni would represent the R. Okay, so for R2 dia dah increase, so kita nak increasekan lagi dia conversion, sebab usually kita nak dapatlah the highest conversion in order for us to have a high amount of the product produced. Okay, so kita kena try masukkan lagi interstage cooling dia in order to increase the XE by lowering the T. So daripada sini kita ada 700 pula. Okay, kat reactor number 2 tu kita nak lower down to 500 before it enters to the next one. Okay, so usually ni akan sama lah. Okay, dekat 500 lah. Alright, so dia akan letak sini. Okay, you cannot get lower than 500 sebab kalau feed temperature is too low, okay, takut dia punya K ataupun dia punya R akan jadi low. Okay, so rate of reaction speed dia akan jadi slow. Okay, that's why you have to maintain at certain temperature. Okay, you cannot go lower down this temperature. Nanti you akan ni lah, what do you call it, cause the reaction to be very slow. Okay, ni this one actually this one kalau you perasan dekat part number 2, dekat slide yang ada curve A and curve B. Okay, this is the reason lah. Dia explain. Okay, so for endothermic pula, okay, endothermic is to achieve higher conversion by interstage heating. Okay, sebab it requires high temperature for a high XE. Okay, so dia inverse balik lah dengan yang ni. Okay, so dia akan ada this one. Okay, so XE dengan T. Okay, so dia perlukan X yang tinggi dekat temperature yang tinggi. Okay, so what you need is to place a heating in between of the reactor. Okay, so this one we just label as R1 reactor 3, and this one is for heater 1 and heater 2. Okay, so if you can see, starting from the feed is a 520 degrees Celsius. Alright, so since it is endothermic, it absorbs heat. Okay, so the temperature released here is lower than the initial one. Alright, same goes here. Okay, so kita kena heat upkan dia. Alright, so 450 kita heat up to 520 again. Alright, kita maintain the same feed here. Okay, sebabnya bila dia berlakunya reaction dekat reactor 2, dia akan lower down the temperature. Okay, the objective is to increase temperature in order to increase the XE. Okay, so you have to heat up again to 420, alright, in order to increase the XE here. Okay, so increasekan XE here. Okay, so how the curve looks like akan jadi. Okay, so it will become like this one. Okay, so for 520, okay, so before this dia go to the right side. Okay, tapi dekat sini dia terbalikkan dia. Dia proceed to the left side. Okay, so for 500 to 450, okay, so this would be the reactor 1. Alright, so it will reach at first XE here. Okay, so for the second XE, kita nak increasekan dia. So we manipulate the temperature. Alright, so we need to increase the temperature back from 450 to 520 degrees Celsius in order to reach a higher XE here. Alright, again, as long benda ni boleh lagi, alright, reach at the higher, so kita try to increase again, alright, from 450 to 520 in order for the reactor number 3 to have a increase of XE. Okay, so inilah dia. Okay, faham ke? This is heater 1 and heater 2. Okay, everyone understand the concept?
Boleh, doktor.
Okay, alright. Dia sebenarnya macam yeah.
Yang exothermic ni high XE, low temperature. Yang endothermic high temperature, high XE
Ya. Tengok balik pada ni je. Kalau you nak senang faham, hafal benda ni. Hafal graf dia. Okay, so you tengoklah endothermic, exothermic, lagi high tinggi XE, temperature yang dia nak adalah lagi rendah. Okay, so bila temperature rendah, XE akan tinggi. Macam mana kita nak control temperature? So of course kita kena put cooling system, nak lower down. Okay. And kalau you tengok pun logik dia, kalau dia keluar sini, kenapa bila kita masuk feed 500 keluar 800? Sebab tengok balik pada prinsip exothermic. Prinsip exothermic adalah dia release heat. Okay, means that so produk yang keluar tu akan jadi lebih tinggi temperature sebab dia release heat. So dia kena cool balik. Macam itulah. Tengok pada graf ni, lepas tu tengok pada sama ada tinggi atau rendahkan temperature. So daripada situ you boleh tentukan sama ada cooling atau heating. Okay. So nak tengok temperature yang di sebalik ni, tengok pada adakah ada exo atau endo. Kalau endo, dia akan absorb heat. So bila dia absorb heat, of course yang keluar temperature akan lebih rendah lah daripada feed. Macam tu lah, dia macam logical mechanism lah. Okay, as long you tahu dia punya prinsip. Macam tu lah. Okay. So this is example sebenarnya yang berkait dengan part 2. Alright. So sekarang ni the question is what conversion could be achieved in example 8-6 if two interstage cooler that had the capacity to cool the exit stream to 350K were available. Okay, this one nantilah kita bincang. This one. Okay, so now we move to CSTR with heat exchange. Okay, so we have for exothermic, remember exothermic kita perlukan coolant. Okay, and endothermic kita perlukan heater. Okay, sebab temperature yang exothermic kita kena dapatkan dia lagi tinggi, yang ni lagi rendah. Okay, so daripada situ you kena tahulah term kalau TA1 ni means that inlet. Okay, temperature yang supply, alright, and TA2 ni adalah temperature of the heating element, coolant element. Okay, so kena tengok TA1 dengan TA2. Okay, actually this is regarding the heat transfer fluid. Okay, heat transfer fluid. Okay, whereby whether we use it to coolkan dia ataupun untuk heatkan dia. Okay, and then we have a T ni adalah T temperature yang untuk reactor. Temperature. Remember you belajar heat transfer, kita ada banyak benda term ni. T, TA1, TA2, T. Okay, so you kena tahulah A ni adalah, A ni memang refer kepada heating fluid, heat transfer fluid element. Okay, T biasa ni adalah T temperature of the reactor. Okay, atau T0 lah temperature pada inlet. Okay, jangan quick confuse. Okay, so kalau you tengok pada sini, okay, katakan we have a coolant system. So TA dengan TA2 adalah TA1 is for the coolant in and TA2 for the coolant out. T besar ni adalah T temperature of reactor. Okay, jangan mix up. Kalau ada T0, ni adalah T inlet lah untuk temperature of the reactor. Okay, jangan salah benda ni. Bila you salah term, nanti bila you masukkan ni, dia akan jadi salah lah. Okay, so the heating transfer fluid involve cooling fluid ataupun heating, macam nak cakap, sama ada dia heating fluid ataupun dia cooling fluid. Okay, so cooling fluid kita guna untuk exothermic and heating fluid adalah untuk endo. Okay, alright. So daripada sini, alright, when there is a heat transfer fluid involved, of course you can tahu what is the rate of heat transfer. Okay, the rate sebab ada titik sini lah, means rate. Okay, from the exchanger to the reactor fluid at temperature T. Okay, so daripada sini, remember this term you pernah belajar is equal to U A delta TLM. Okay, ni dekat you belajar heat transfer, and you also baru je belajar semester lepas dalam heat transfer and mass lab CHE502. Okay, kan you ada belajar kan dekat apa nama benda alah tu, heat exchanger dia lah. Okay, you ada belajar kan, so ada TLM. Okay, so benda ni adalah referring to the from the exchanger to the reactor fluid at temperature T is defined as this one. Okay, so this would involve the heat exchanger lah, kita panggil heat exchanger. Okay, alright. So we have a T minus TA dengan ni. Okay, so what is U? U is the overall heat transfer coefficient. So U ni adalah overall heat transfer coefficient. Okay, so this is U. Okay, so A ni apa dia? Kena remember what is this? It is a heat transfer area. Okay, maaf tulisan saya makin lama makin kronik sangat. Okay, and then we have a temperature. Okay, so this will be the temperature. Okay, alright. Okay, faham up till now? Refresh, recall what you learned before this. Okay, so that's why fundamental of chemical engineering is very important. You kena tahu relate kan apa yang you belajar heat transfer, mass transfer, okay, dengan reaction 1. Okay, it's an integration of knowledge orang panggil. Okay, dia takkan stand alone. Dia akan somehow akan berkait. Okay. So that's why waktu saya ajar heat transfer, senior you dulu-dulu, I memang tekankan macam mana nak gunakan equation tu, macam mana nak senang prinsipal dia, mekanisme, okay. So that sampai bila-bila pun you akan senang ingat. Okay. So this is the energy balance. Okay, this is the one, okay, yang you akan belajar lah. Energy balance on heat exchanger fluid, we have a rate of energy in by flow. Alright, remember selalunya Q is equal to M Cp delta T. Okay, so this is the heat. Okay, then rate of energy out by flow. Okay, so we remember TA2 ni adalah berkaitan dengan heating fluid. Alright, heat material lah, heating fluid material. Okay, TR dan T reference. And then we have minus with the rate of heat transfer from exchanger to reactor. Okay, so this is the heat exchanger. Okay, so energy being supplied, okay, katakan this is here. Okay, energy being supplied in and energy out, you kena take into consideration elemen dalam sini. Alright, heat exchanger. That's why you kena minus dengan heat exchange here. Okay, so QMCP TA1 minus TA2. Okay, whereby you can what do you call it, simplifykan ni kita boleh what do you call it, cancel out. Okay, what remain is this one and is equal to 0 because this is occur in a steady state. Okay, so just put it this one at the right side here. Okay, you will have this equation. Alright, so this would represent the heat transfer. Okay, heat exchange there. Alright, so wave Cp is the heat capacity of the heat exchanger fluid and TR is the reference temperature. Okay, so this is heat exchanger fluid lah, coolant ataupun heater. Okay, so rearrange the equation, we get heat transfer to ACSTR. Okay, remember Cp ni sebenarnya bukan Cp pada reactant or product tau, bukan. Ini adalah berkaitan dengan heat transfer fluid. Okay. So rearrange the equation above, we get the heat transfer to ACSTR. So kita just rearrangekan dia, kita dapatlah this equation. Okay, whereby kalau high coolant flow rate terlalu tinggi, kita boleh assume TA1 is equal to TA2 is equal to TA. Okay, TA yang masuk ni, remember yang masuk sini, okay, akan sama juga dengan TA dekat dalam sini. Okay, so you can just simplify Q is equal to UA TA minus T. Okay, so this one lah, you can simplifykan ni jadi this one. Okay, you have two choice lah, sama ada you nak guna this one ataupun you guna this one. Okay. Okay, so from here, remember this is the equation yang I suruh you ingat sampai bila-bila sebab this is general equation. Okay, so sekarang ni kita boleh assume WS adalah 0 tapi Q we need to replace dengan heat exchanger punya, which is UA, this is equal to UA TA minus T. Okay, so after you rearrangekan ni, okay, you akan dapat FN0 ni dia akan cancel kat sini tapi FN0 ni kena remain kat sini. Okay, sebab kenapa? Okay, katakan this one you bawa ke sini lah. Okay, I mahu tulis balik. So this one you bawa ke arah sini. Okay, so this would be ada Q. Okay, so Q this is FA0 kan. So FA0 kita divided dan the whole FA0, that's why dia akan bawah ni ada over FA0. Okay, sebab FA0 ni dia bawa ke bawah here. Okay. Okay, tapi this one dia dah cancel lah. Dia dah over FA0. Okay, sebab dia dah ke bawah. So that's why remain here and therefore UA TA minus T. Okay, so this one is the Q. Okay. Alright. So you will have this one lah, the equation here. Alright. So this one, remember, dia boleh simplify. This can simplify to delta HR X T. Okay, that's why dia dah simplify jadi pendek ni. Alright, this is delta HR X dekat any temperature. Okay, so you arrange kan in order to get XEB, the conversion of energy balance. Alright, from the energy balance, so you will get this one. And then from here also you can rearrange in terms of T, you will get this one. Okay, so far faham ke?
Boleh sikit-sikit Doktor.
Okay, so this is for energy balance conversion, nama dia, for non-adiabatic. Okay, so apa-apa pun you kena tahu guna this general equation. It's just that kalau dia adiabatic, you cancel this one zero. Tapi kalau dia non-adiabatic, you kena consider dia ada UA times TA minus T. Replace dia ni. Apa-apa pun you kena tahu general equation ni saja. Okay. And then juga equation ini. Ni represent apa. Okay. So that you can simplify like this one. Okay. And then you rearrangekan sahaja. Rearrange in term of X. Alright. And rearrange in term of T. Itu sahaja sebenarnya. Sebenarnya basically dia back to the, itulah fundamental dia balik pada energy balance dia. Okay, cuma kita manipulate apa yang ada info kat sini. Okay, alright. So for summary for design algorithm CSR with the heat exchange. Okay, so this is for non-adiabatic tau. Okay, remember masa adiabatic pun kita ada case 1 and case 2. Dia lebih kurang juga sama. Okay, so let's say given FA0, CA0, K0, E, CPA, delta HRX, delta CP equal to 0 dan theta I is equal to 0. Okay. So V is equal to, kita tengok balik pada algorithm dia, start with the design equation. Okay, so this is the volume of the CSTR. Okay, and then you need to get the rate law. Okay, depending kalau dia boleh can be reversible ataupun irreversible. So that's why you need to know how to derive the rate law for both of directions. Okay, and then you need to relate with the K. Okay, so kalau this is K for irreversible. Okay, kalau for reversible, you kena guna K yang besar, which dia akan relate to the delta HRX instead of E. Okay, yang ni kita E lah. Okay, and then go back to the what is CA, sebab this one kita pecahkan RA dia ada KCA kan, so what is CA, so automatic tengokkan pada dia. Okay, kalau this is for fluid lah, kalau the gas, you kena ada epsilon lah. Okay, tapi this is CSR, usually kita akan ada dalam bentuk fluid. Okay, so masukkan dia V is equal to FA0 X KCA0 Y minus X. Okay, so now you kena remember X conversion adalah berkaitan dengan temperature. Dia adalah temperature dependent sebab dia adalah non-isothermal. Okay, that's why you kena go back to get what is XEB lah. Okay, so kita need to calculate the T. Okay, let's say X is specified. Alright, dia dah bagi dah, kita nak dapatkan X, nak dapatkan V dekat contoh X 0.9. Okay, so X dia dah diberi, so that's why you boleh guna information X here. Letak je X in order for you to get the T. Okay, macam you dapat T ni, rearrange daripada energy balance lah. Okay, so daripada situ, sebab apa you kena dapatkan T? Sebab T ni akan relate back to the K. Sebab T here, information ni kita tak ada. Okay, sebab T is not specified right now. Okay, so masukkan nilai T. Alright, here you will get the nilai of K. Alright, so once you get this one, you will be able to calculate the V here. Okay, alright. Okay, this one, let's say if the V is specified, volume is given. Okay, so bila volume is given, you kena start lah dengan mole balance XMB. Okay, remember this is a conversion from the mass balance. So how do you get the mass balance? Starting from the design of equation. Okay, so design equation ni you kena tengok lah, which is V is equal to FA naught X over RA, negative RA. So you pecahkan, V is equal to CA naught V naught X. Okay, negative RA is KCA naught 1 minus X. Okay, rearrangekan dia sampai dapat in term of this one. Okay, so daripada situ, okay, this one you kena dah tahulah sebab this you learn in topic number 4. Alright, which is you dah rearrange daripada mass balance, you akan dapat tau K over 1 plus tau K. Okay, so at this case, kita tak tahu K ni sekarang ni adalah berkaitan dengan temperature kan. Okay, so from here, you kena calculate what is X and T. Okay, for example, that's why here we can get two kind of X. Okay, which is you akan dapat XEB. Okay, you akan dapat XEB and also XMB. Okay, so bila you dapat dua ni, you akan dapat intersection lah untuk calculate what is T dengan what is X. Okay, so you kena construct this what they call it, plot lah. Okay, you kena letak lah. So information yang kita perlukan adalah, okay, katakan this is XMB and this is XEB. Okay, tengok balik. Kalau ni kita akan dapat SMB, kita dapat K kan. Alright. So K ni sekarang ni bila K adalah berkaitan dengan ni. Alright. So K ni you kena ada specific temperature lah. Temperature apa yang you nak letak. Okay. So katakan this is, we have a T at certain 300 to 350. Okay. So you will have a different K. So masukkan balik K, you akan dapat different XMB here. Okay. So XEB ni pula you akan, bila you varykan T, alright, you akan dapat different XEB. Okay, so automatically you can plot, you akan dapat intersection of T dengan X temperature. Alright, okay, faham ke tak? So far tak adalah 100% faham, tapi boleh catch up tak sikit-sikit?
Boleh ada.
Okay, so this is case 1 and case 2. Okay, apa-apa pun tengok balik pada equation, tengok balik value apa yang you kena cari. Okay, alright. So, saya rasa kita rehat sekejap lah, 3 minutes. Boleh?
Boleh doktor.
Okay, rehat dulu 3 minutes. Okay, boleh sambung ke sikit je slide?
Boleh dah.
Okay, so nanti kalau tak sempat sebenarnya saya nak go through tutorial macam sebelum ni kita buat saya macam discuss sikit, nanti saya suruh you buat lah dulu tutorial. I macam bagi brief idea, okay question ni untuk apa, question ni untuk apa, okay. Kalau I tak sempat tu I record yang tu lah, okay boleh ya?
Boleh
Nanti,
doktor.
nanti you refer lah pada record tu masa nak buat tutorial nanti. Okay, tutorial saya bagi you sampai minggu depan hari Khamis nanti baru kita bincang lah Okay, tak payah rushing. Itulah, saya kan what do you call it, hutang dengan you all nak bincang MTA dengan assignment 1 tapi Allah macam singkat. So maybe saya akan buat untuk hari Selasa lah kot yang tu. Okay, sebab kita dah habis ni. And saya ada satu benda yang tak cover, yang polymath tu. Sebenarnya benda itu maybe saya akan record jugalah benda tu sebab itu just untuk guna untuk assignment 2 saja. Macam mana nak buat polymath. Sebenarnya dia punya coding semua dah ada dalam Fogler tu. You boleh tiru je, cuma ubah sikit-sikit je. Tapi tak apa, nanti saya akan bagi recorded punya yang version minggu ni. Itu je lah untuk part assignment 2. Polymath tu you download je trial punya. Dia boleh tahan 10 hari, 3 hari je, as long ada result tu okey lah. Okay. Okay, so kita continue. Okay, now is PFR, PBR with a heat exchange. Okay, so I recommend you untuk chapter topic 7 ni, eloklah kalau you refer to Fogler sebab dia ada banyak example. Okay, so you boleh try to buat example dia, okay, in order for you to have a good understanding lah on this topic. Okay, so in PFR or PBR, the concentration and reaction rate vary along the reaction length. Very long the reactor line. Q will likely vary too. Okay, sebab kalau PBFR dan PBR ni, okay, kalau kita nampak, okay, there is a feed here. Okay, so there is a difference of the volume here. Alright, so for each of the volume here difference, it will have a different Q heat. Okay, so consider a tubular reactor in which heat is either added or removed through the cylindrical walls of the reactor. Okay, so we still apply the same equation. Okay, Q is equal to U A T A minus T. Okay, but in this case, if this is a PFR, so kita kena consider there is a change of the volume. Alright, so bila ada volume change, of course Q ni akan change. Okay, so that's why we have a delta punya symbol here, okay, whereby A ni kita boleh pecahkan dia sebenarnya. Sebab apa? Okay, so we assume that area is equals to A times the V. Alright, so V is the volume. Okay, this is a sphere which is pi d squared L, and area is pi dl. Okay, pi dl, and this is pi d squared L. Okay, so you will have the A. Alright, A is the heat exchanger area over with the unit volume. Okay, that's why this one usually you will have a unit of 1 over m lah. Okay, m2 over m3. Okay, so whereby dia change pada V tapi pada A ni dia tetap sama. Okay, that's why dia tak ada terms of A ni. Alright. Okay, sebab dia assume area per unit volume will be is fixed along the reactor. Okay, so daripada situ, alright, tengok balik, remember yang awal-awal part 1 we learn about Q plus with the FRHI minus FRHI. This is before kita expand in term of the heat capacity and heat of reactions. Okay, kita relate dengan mass flow. Okay, so the energy balance is this one, represent I is for the at V, and this one is plus delta V. Okay, is equal to 0 sebab this is a steady state lah. Okay, so Q sebenarnya ni lah yang kita akan masukkan balik dekat this part. Okay, so as shown in figure 12-1, the heat flow to reactor is represent this one. Okay, so substitute the above equation into energy balance in equation 12-1 and doing various mathematical manipulation, we can get this one. Okay, so kalau ni kita ada delta V, that's why nanti you akan dapat dV here. Okay, so this is come from the energy balance. Okay, ni daripada part 1 tu. Okay, tapi jangan risau, you don't have to show apa benda ni. Nanti kalau ada apa final assessment, katakanlah kalau ada final assessment benda ni, kami akan provide teruslah this one. Okay, this equation. And then this one is for the kalau PBR, which is packed bed reactor. Okay, kita ada catalyst yang being packed on the reactor. Okay, that's why kita consider weight instead of volume. This one is the weight. Okay, weight of catalyst ke apa ke, alright. So same je, alright. But this one we don't have a delta CP lah. Okay. And this dW, alright, is equals to, I tulis kat sini, dW is equal to rho B dV. Okay. So this is we call as bulk density. Bulk density. Okay, kita bukan kira pada single density of the catalyst, kita kira the bulk, alright, secara menyeluruh, ataupun dalam kata lain density of catalyst bed. Okay, so this is the heat exchange. Okay, so at the end inilah yang kita nak tengok. Okay, so this, okay, yang tadi ni, this represent with the Q untuk what do you call it? Q generated. Okay, this one is heat Q generated. This one is the heat Q removed. Okay, that's why the minus here. Okay, so that's why we have a QG dengan QR. Ni generated and this is removed. Okay, so dia dapat benda ni lah at the end. Okay, so here, okay, inilah yang penting lah part ni. Ni yang you belajar yang previous slide. Okay, so kalau dalam molar flow rate dia akan jadi macam ni lah. Okay, alright. So from here, this is system lah. This is for the PFR and this one is for PBR. Okay, sama je lebih kurang dengan CSR. It's just that dia ada CSR Q is equal to UAT A minus T. Yang ni dia ada over V. Okay, sebab dia ada difference of volume. Okay, alright. So dekat sini pula dia ada what do you call it, bulk density, right? Whereby the bulk density is not equals to density of catalyst. Okay, so inilah. Alright. So saya rasa saya stop dekat situ sahaja sebab you ada kelas kan after this. Okay. So saya saya just nak outline lah example apa yang you boleh refer. Okay, so you boleh tengok dekat example, alright, 11-3, alright, dekat page 512. This is for 4th edition and this one is the 5th edition. 5th edition, sorry, ini 5th edition. Sorry, ini 5th edition and this is 4th edition. Okay, so ini boleh tengok kat example 8-3, page 490. This one is example 12-1, alright, dekat page 548, and then this one is 8-4, page 497. Okay, so this one you boleh tengoklah contoh pada adiabatic versus non-adiabatic design. Okay, so for example lagi satu you boleh refer juga dekat example 11-4, alright, page 519. Okay, and also kalau 4th edition 8-6 example page 513. This one untuk calculate adiabatic equilibrium temperature. equilibrium temperature. Okay, itu untuk nombor 1, nombor 2, nombor 3. Okay, nombor 4 pula you boleh tengok dekat example 11-5, okay, page 524 ataupun kalau dekat formula 4th edition 8-7 page 517. Okay, so yang ni pula dia akan relate to number 3 yang ni example, alright, but has a interstage cooling. Okay, so dia akan relate lah 11.4 to 11.5. Okay, so I rasa I tak sempat nak discuss tutorial secara general, tapi I akan record yang benda tu. Okay, untuk for your own use lah, for tutorial bila you buat nanti. Okay, so you ada guide sikit. Alright, ada guideline sikit. Okay, so ini adalah most important formula yang you kena tahu. Okay, tengok balik lah. Ni I dah explain dah sebelum ni. Okay, I think that's all for today. Are you okay? How is the progress of assignment 2? Are you able to do it? To answer it? Okay tak assignment 2?
So far okay my good.
Okay, so far okay. Okay, kalau ada apa-apa nak saya need further clarification, boleh je WhatsApp saya tanya, okay? Tapi benda ni sebenarnya senang je, soalan dia nampak panjang tapi dia sebenarnya straightforward je jawapan dia. Okay, dia guna balik apa yang you belajar. Okay, dia tak ada twist-twist sangat pun. Yang penting you kena pandai cari data, cari enthalpy, cari CP, masukkan balik semua. Macam tu je lah. Lepas tu analysekan dia, jawab apa yang dia nak tu. Okay, itu sajalah, and saya akan record untuk tutor punya guideline lepas ni. Okay, I think we can end our class with tasbih kifarah and surah